All right, how's it going, everybody? We're here on Monday at the beginning of week 4. We're going to wrap up our chapter 6 topics here and start chapter 7 tomorrow. Just as our kind of generic reminder of where we're at, chapter 6 is our first chapter of applications of integration techniques. We've seen that we had 3 sections of computing various volumes, so a really geometric couple of sections. We talked some physics problem, which included officially was named work. We looked at some spring forces. I think in the homework you guys saw some electromagnetic forces, some resisting the force of gravity, stuff like that. In the previous section, our last application for this chapter is average value. The good news here is that this is pretty easy. I tried to pick up some of the hardest questions I could think of asking that are associated with average value, but fortunately it's conceptually pretty easy. And the only tough stuff here is I've just set up some problems that are going to have some difficult algebra and some difficult integration, but I think conceptually these are pretty easy here. The probably more important one is our section 7.1 tomorrow when we talk about integration by parts. This one's a bit tougher of a section. It's a section that depends heavily on our ability to practice to develop intuition about smart choices to make for substitutions. It's certainly the bigger of the 2 sections for you to be worrying about associated with week 4 content here. Integration by parts is just extremely important as a technique. It's if I had to pick like a single few things that are more important than everything else in this class, integration by parts is very high on the list. So section 7.1 is super important and not. I don't want to be like it's really hard because it's not, but it's easy to do, but it's hard to be good at. That's what I'll say about section 7.1. It's easy to do it on your first couple examples, but to develop the appropriate intuition definitely takes a little time and effort. So we want to be spending a little bit more of our time and effort on that one there. To that end, today I've set up 3 examples for us to work through today, but the third example will actually be dependent on some 7.1 stuff. I set up examples 2 and 3 to be comparisons between each other, but we want to see that if we try to make our problem slightly more appropriate, we will lose our ability to perform the integration, and we will learn in 7.1 exactly how to do that. So our last example today might be one that you're maybe in a sense slightly unprepared for if you're not haven't read through your section 7.1 section, but I'm going to throw it into today's video anyway, just so that we can kind of see part of the reason, like why do we care about the new techniques we're going to get in chapter 7. So let's go ahead and start with this stuff here. So we're talking average value today. And as I've said a couple times, said it in the notes, said it in last week's message, said it already today, it's pretty easy. If you can compute an average, then the concept is the same for average value. When we compute the average of a collection of numbers, if we have n objects, and if we name each of the n objects one x sub I, so x sub 1 is the first, all the way up to x sub n is the nth, then all we do to compute an average is we just add up all the objects, the sum of them, and we divide by how many objects we had. We're going to do an incredibly similar thing when we compute the average value of a function. The only difference is that because we're in calculus class, we know that we perform sums by performing the infinite sum, adding up all of the individual heights of our Riemann sticks. So that's still a summation up top. It's just the integral version of a summation rather than the true summation version of a summation. And rather than dividing by how many objects that we had, we're just dividing by the width of the interval that's being considered. B minus A is how wide our x interval is that we're interested in. So this is really just an analog of exactly what you guys are already used to for computing averages in your life. Add up a bunch of stuff, divide by how much stuff you had. That's my most layman's terms description of an average, and that verbal description fits both of the formulas that you see on the screen right here. So before we get into any problems, I do want to really make sure that we have some intuition about what it is that we're doing here. What you should see here is that this average value of the function is the area divided by width. And area divided by width is exactly how we compute height when we think about our area formula. If area is width times height, you could just think of dividing width to the other side, and area divided by width should be giving us the height or the average height of our function. Notice that this formula really only makes sense if you're using constants, right? These don't make as much sense to us interpretably if we have functions that are in here of x rather than just a constant. So here you should notice that this is just a single height, And so therefore, it's actually more appropriate for this to really be stated as the average height right there. But again, the point is that we are taking our most basic geometry equation and simply dividing width over to the other side. And that's exactly giving us that area divided by width, that's our denominator, I can't highlight it, is exactly equal to the height, the average height of the function, the average value of a function. Remember, outputs from functions, the f of x value, those are represented vertically graphically. So that is the height of a function value. We're trying to add up all the heights, divide by how many heights we had. That'll give us our average height here. The other thing that I think it's really good to do visually, geometrically, when we look at our graphs is to think of the area that's under, when we're thinking about what the average value is, that you should picture all these curves that we've computed an area underneath so far. You should picture all that area underneath the curve as water that is in a 2D container, where that 2D container is always the y-axis and your two x boundaries, your left and right bounds right there. There's always some curve that's in between these things, and we're computing the area underneath. What you should be picturing for average value is that the area underneath the curve, bounded below by y equals 0, bounded left and right by x equals a and x equals b, the area underneath that curve and within those three boundaries is water, but it's water that's in motion because we see that some parts are high, some parts are low. What we want to think to ourselves is if we were really to allow that water to settle and come down to rest, what would be exactly the height of the water? That is the average value of our function in that case. So that's just a good visual move for us to do to help us get an idea of like guesses that we might want to make that are in association with each of the example problems that we're going to see here. So picture our area underneath the curve as water. And when computing the average value, the question is, what would the height of the water be if it were allowed to come to rest within its container? That's the exact same thing as when we say we're computing average value with integration. So let's go ahead and look at a few examples here. And again, this isn't hard. To directly do this is just to compute this formula here, where as you can see, it's nothing more than just performing an integral, but also just then dividing by a number. That's the only extra step that's here computationally. So I'm not even going to do a problem that just says compute the average value of this function over this interval. There's not much exciting. You can just read that example in the textbook. I'm going to try and do some slightly more exciting examples here today. Example 1 and 2, you should be able to do. Example 3, you technically can't do until we've covered 7.1. So our third example is sort of our preemptive example in anticipation of tomorrow's video. So example 1, we're being given the velocity of a particle. What we want to do is determine what time the particle is traveling at its average speed. So that we want to first determine what is the average speed of the particle over the interval 3 seconds to 8 seconds. Once we know what the average speed is, my next question is, when were we traveling at that speed? All right. So let's first kind of get a visual sense of what we're looking for here. And to do that, I'm going to pop on over to Desmos. So we can see our equation here is like y equals x squared minus 10x plus 26. So over here in Desmos, let's go ahead and throw that guy in here. We are looking at y equals x squared minus 10x plus 26. All right, so if I go to home here, I can see where my curve of interest is at. I know that I am only interested in seeing this curve between 3 and 8. And so I can say 3 less than x less than 8. Right? That's only the part of the curve that I'm interested in. And if I wanted to actually make this look all extra nice for myself now, I could maybe do something like x equals 3 and do that from 0 less than y less than, let's see, if I plug in 3 there, 9 minus 30 negative 21 plus 26 is 5. That should be my height right there. And I could also do x equals 8. And if I plug in 8 into this thing, this will go from 0 less than x, or less than y, less than, if I plug in 8 there, 64 minus 80 is negative 16 plus 26 will give me a height of 10. And so what I'm picturing here for myself is I am picturing, and man, maybe even let me change these so that this actually feels like what I feel like this is. That's the water, the blue stuff there, right? I'm picturing these guys to be my other boundaries of my container here. I'll make them black. And so what I'm picturing is this is some water inside of a big container here. What I want to know is if I were to let this water come to rest, then what would the height be? And I'm picturing that we're going to see some height that's, maybe down here at a height of like 3 or 4 or something like that. So I'm going to go ahead and just cut this out and drag it over into Microsoft Word here. Let's come back to Word. And so let me drag this guy down. So here's my Desmos clip right there. And this is kind of our guide for this problem. So first, I want to do the things that we should basically always do for the rest of our adult mathematical life, which is you should basically guess answers to things all the time, like forever. Guessing should never be the last thing that you should do, ever, because we want to do more than that. You're a mathematician now. But also, guessing should always be the first thing that you do because you want to understand if you're developing good intuition or not. So my first move here is just to guess. I'm picturing, if I were, to picture the wall of this container going up forever, maybe, I'm picturing to myself, if I were to let all this water come down to rest here, I'm picturing for myself that we should probably be getting an average value that's something like that. That's just my guess. I may be off by a unit vertically or horizontally. So this might be my average value estimate right there. I'm just trying to make a visual guess for myself. But notice in this problem, I wasn't asked what was the average velocity. I was asked at what times was the particle traveling at that average velocity. And what I can see now based on this average velocity height right here at this average time is that it looks like there's probably going to be 2 locations where that happens, right? So I'm thinking to myself, this should be my time 1 of interest, and this is going to be my time 2 of interest. Our goal is to identify those 2 t values that are sitting down there. At what time was our particle traveling at its average velocity over that time interval right there? So let's go ahead and first compute the average velocity so we know what the height is. Then we'll find out at what times our parabola intersects that height. So our average value statement right here should be, we're looking at 1 over b minus a times the integral from a to b, in this case v of t dt. We can fill out all of our parts here. We've been given an upper bound, we've been given a lower bound, we've been given a function of interest. And so it looks like here, 1 over 8 minus 3 times the integral from 3 to 8 of t squared minus 10t plus 26. I think I've made a nice bit of fraction annoyance for us to come up with here, so we'll get to deal with that in a second. And now we're just computing. So notice like right away, just to get our average value here, there's not too much exciting that's going on. Like this is integration that you guys have done. And the only other component is we're introducing a constant multiplier. And that's it. Like to do the average value, to compute an average value directly, not a lot of excitement going on here. So I'm getting 1/5 times, and it looks like we're going to be getting here the integral of, the integral gives 1/3 t cubed minus 5t squared plus 26t. And we are evaluating this from t equals 3 to t equals 8. All right, I'm actually going to have to do some work here. This is kind of annoying. Looks like I'm going to be getting 1/5 times, and I'll give my 2 groupings in here. Let's see, 8 cubed is not 216, right? 8 cubed, 512. I was off by half. So I'm going to get here a 512 over 3 minus 8 squared is 64. 5 times 64 is 320. Plus 26 times 8 is 208. There's my upper bound minus my lower bound evaluation. Notice here 1/3 times 3 cubed should just be 3 squared, so that's 9. 3 squared is 9 times 5 is 45. 3 times 26 is 60, 78. Okay, so it looks like we're going to have some stuff in terms of thirds right here, but overall this value doesn't seem to be too terribly bad here. Oh, so that 1/5 is going to be sitting out there also. So I am seeing here, I've got a 512 over 3 minus 320 plus 208 minus 9 plus 45 minus 78. And then we're going to divide that by 5. And by the way, that is giving me here, I'm seeing that this is exactly 1/5 of, I'm getting 100 over 6 right there. And that will be giving me 100 over 30, or 10 over 3, or 3.3 repeating for my actual value right there. 10 thirds, that's a really nice, good, clean fraction right there. So that's kind of really convenient for us that we get something nice right there. So what we've done so far is we've now found that the average value of our function, the height of the function, is going to be at 10 thirds, 3.3. And by the way, I actually kind of nailed this. My guess right here is at 3.5. Like I'm actually crazy close with my guess right there. I guessed halfway between 3 and 4. And I'm going to be super honest with you guys. I didn't even compute the answer to this problem before I set it up. I just guaranteed that I'd be able to do it and didn't actually get them. I nailed that right there. So my guess was good. So again, do these guesses, because the point of guessing is you should feel good about yourself after you've done a guess and been like, okay, apparently I'm thinking about this correctly because I computed an answer that's wildly close to what I guessed right there. I just wasn't ever going to possibly be able to guess the technicality of like the 3.3 repeating kind of thing. So what we've done so far, again, is we've only found a y value so far. This is the average height of a function. That's a y value. What we're interested in, so maybe I'll call that v average, is 10 thirds. What we wanted to know is when, at what times, what inputs into this function give us the output of 10 thirds. So what we're going to go do now is just strictly some algebra. I know that I have a line of height 10 thirds. I want to know when does it intersect this parabola right here. So we have the lines v of t equals t squared minus 10t plus 26. And we have that our v average is 10 thirds. I want to know when these are the same as each other. So let's go ahead and solve for that. I know that if I'm ever solving some quadratic that I don't really want to solve, my two options are either complete the square or quadratic formula. I kind of go back and forth as to which one I think is the better or worse one here. I'm thinking to myself, 26 is times 3 is 78 thirds. Is that right? 60, 78? Yeah, 78 thirds. So 78 thirds minus 10 thirds is 68 thirds. If I were to complete the square here, I would see that we're going to get, we really wanted 25 on the end there. So that tells me t squared minus 10t plus 25 minus 25 plus 68 thirds equals 0. Those terms are going to give me t minus 5 squared. The second grouping of terms, I know that this is going to actually be 75 over 3. So that's negative 75 thirds, positive 68 thirds gives me minus 7 thirds equals 0. And now I can go ahead and solve for those two locations that we're going to be landing at right there. It looks like we're going to be getting t minus 5 squared equals 7 thirds. T minus 5 equals plus or minus root 7 thirds. 7 thirds, by the way, is like 2 point something. So the square root of it's going to be pretty small, like 1 point something. So I know that when I do my 5 plus or minus root 7 thirds, that's going to be giving me 5 plus or minus. That's going to be like a 1 point something right there. I guess I could go to the calculator and actually get these. I do like these as exact answers though. So 5 plus the square root of 7 over 3, 6.527. And 5 minus that square root of 7 thirds, 3.472. But again, definitely realize that it's guaranteed to be the case that on our first test, I'm going to say to you things like, be sure to give exact answers. In that case, I am more interested in 5 plus or minus root 7 over 3 than I am in this, partially because Desmos will tell you this. Desmos will not tell you this. I want to know that you can actually do the math here, come up with what those values are going to be on your own. And so my estimates here are about 3.5 and 6.5, by the way. And again, coming over here to notice about 3.5 is about where this is at, and about 6.5. So my estimates here, again, visually, were incredibly close, left and right horizontally as to where they should have been, and vertically right there. So use graphs for these kinds of things to help you out with these. It's really, really helpful for you to see that and be like, oh my gosh, my guess was within 0.1 of the correct answer. Like, that's how you get to feel good about your answers. So make guesses. That's for you to feel good. That's not just for no reason. I appreciate the make a guess, and then see if you're right or see if you're wrong, right? So in this one, we need to first compute the average value, then determine at what times were we traveling at the average speed. And we did that by just doing a little bit of algebra right here. So hopefully you guys recognize your algebras right here. And if not, I have full confidence that you are going to go back and remind yourselves that you know about either completing the square or using the quadratic formula to come up with these guys right here. Right? So there's my example one. And in example one, the thing that was exciting here was that rather than me just saying, find the average value, I said, find a time at which we achieve the average value. So that added a second layer into it. Very similarly, these next couple problems are not going to just be directly compute the average value. It's going to ask a more indirect question than that associated with average value. So let's bump this over to a new screen and look at this guy here. So a question that a medical person might be interested in knowing is, and actually we'll talk about why this technically wouldn't be a super appropriate computation to do as a medical professional, but that's okay. Suppose that the concentration of a certain drug in milligrams per liter in a person's blood, T hours after being intravenously given one dose of the drug, is given by, and let me tell you my notation here. So our time is measured in hours. That's our independent variable. I'm calling this a C of t function for concentration based on time. And you can see here that it's C sub I, where the I stands for the fact that this is going to be intravenously given to the person. What we're going to discuss is that is going to have a different relationship with the quantity in your bloodstream as if you were to have taken the drug orally or in any form really that's not injecting it directly into your veins. We'll talk about why we get different kind of models that predict those, like kind of how we'll see the concentrations change over time. So that C sub I is the concentration based on intravenous delivery over time of a drug in our system right here. Our question is this. We want to wait until the average value in our blood over time is 5 milligrams per liter. The question is, how long do we need to wait until we have experienced over the full amount of time that it's been in our system an average exposure of 5 milligrams per liter? So in this case here, we're not looking to compute the average value. We've been given the desired average. The desired average is 5. What we want to know is how long should we wait until we get to that particular average. So let's again set up our generic statements, fill them in with the parts that we know, see what we can do. And it looks like to get our average here, our average concentration, that should be 1 over b minus a times the integral from a to b of c sub I of t dt. We know a bunch of these parts, but we don't know all these parts. I know that the desired average concentration is 5 milligrams per liter. In this case here, we're really thinking of our... Yeah, exactly, Coffee Gopher. So basically here, we're all going to be smart and pick a smart lower bound of 0 because the number of hours elapsed. But the point is here, we don't know what our upper bound is, right? We don't know for how long we want to wait. So we're doing this from 0 hours up to b hours we want to have. And b, by the way, is just I don't know, I'm leaving it as b because it's our upper bound. If we wouldn't have known the lower bound, we would have left the a blank in there. And so here I'll get the 20e to the negative 0.05t, right? So in this case here, we did know the output from the average computation to be 5. That's our desired average. We don't know for how long we want to wait for. And so here's the thing that I'm kind of picturing. I want to pop back over to Desmos before we actually do this so that we can make our estimate. I should keep this graphical right here. I want to keep on doing these ones here. So if I come over here in this problem now, we are interested in our 20e to the negative 0.05t. And hopefully what we all remember from algebra class here is that we have this exponential decaying function. You should remember from algebra class that the decay is because we have a negative on the power of the e. It's not going to decay super quickly because that 0.05 for our decay rate says a continuous decay rate of about 5% per hour. The 20 is our initial value right here. So you can see that at time 0, we do have 20 milligrams per liter. So if the typical human body has, what, 6 liters of blood or something like that, we must have been given about a 120 milligram dose if we're going to have 20 milligrams per liter in our blood at that first starting point right there. So I'm just going to snag a picture of this so I can kind of mark it a little bit on our actual one over there. And very importantly, we're going to want to compare this to the next example that we're going to do because I'm going to start you with a more typical computation that's been done in the second one. But in the second one, it's going to have a more difficult integration to do. That's going to be our kind of trade-off right there. We're going to get a better model, but a little bit worse math right there. So, ooh, that didn't quite do what I wanted to do. Keep hitting enter. There we go. Okay. So again, I'm kind of making my estimate right here. I know that I want my average to be 5. So 5 should be right here. There's my average value. And what I'm picturing is I need to go out far enough that if I'm picturing this being water, I'm picturing that this is all of our extra water, and it needs to all have room in this gap out here between my dashed line and my function. So I'm kind of picturing like we might be going out like out to here. Like I'm not going to be terribly surprised if we get an answer somewhere in the ballpark of like 100. I kind of think it's going to be at least at the edge of my graph. I kind of picture something between like 70 and 100 for my guess right there. And again, I'm just guessing, but it's nice to see that your guess is right there. So it's just my freestyle guessing right there. I don't know, something a little bit maybe beyond the edge of my graph that I've produced right there. I think maybe even 100 is a little too high. Maybe something like 70 or 80 or 90 right there. So let's go ahead and see. And again, in our next problem, we're going to do something almost exactly like this, but we're just going to give the person the drug a different way. We should expect to see a different curve, and it's going to influence our ability to predict our answer here. So what do we got? We want to know what B is. We want to know for how long is this going to take. B is a time. It's our final time. So let's see if we can do some solving here. So, by the way, that's not an equals. That's a multiplication symbol right there. So here's some things I'm seeing. One, this is just a constant multiple. So that's 1 over B. So I think my first move is, I don't know. I mean, I'm trying to just do this integration over here. I'm going to multiply B over to the other side here. So it's 5B. I'm also going to take this 20 as a constant multiple, and I'm going to divide it to the other side. So 5 divided by 20 is 1/4. So I think 1/4 B equal to this integral here. Oh my gosh. There we go. Can't abandon my DTs there. So again, two constant multiples that I did right there. 1 over B is a constant, so I multiply B on both sides. So B is now on the left in the numerator. 20 was a constant multiple inside the integrand. I divided both sides by 20. 5 divided by 20 is 1/4. So 1/4 B, or B over 4, is my left-hand side. On my right-hand side, that's a pretty easy direct integral right there. Technically, if I wanted to write this out, by the way, as a u sub, I could do u equals negative 0.05 t, and du is going to be negative 0.05 dt. I'm going to divide by this negative 1.05. That's going to give me negative 20 du equals dt. And that's going to be my substitution here. So it looks like I'm going to get this 1/4 b equals negative 20 integral from 0 to t equals b. I'm keeping track that it's still t of e to the u du. And again, I typically wouldn't write out the u sub for this because I can see this little easy chain rule there. But it's not a bad idea. Negative 20. Here, we're just going to get out the integral of e to the u is just e to the u. And we're going to evaluate this from t equals 0 to t equals b. So let's do two things here. One, let's convert back into t land. Two, let's divide by the negative 20. So I'm going to get a negative 1 over 80 b on this side. Over here, I've got e to the, now u is negative 0.05t, evaluated from t equals 0 to t equals b. And so it looks like this is really e to the negative 0.05b minus e to the 0, and that's just going to be 1. So we're getting close to a good algebraic expression here. So we just did a whole bunch of work, but I mean, what's our situation right now, right? Now we're in an algebraic pickle right here. Here's currently my issue. My issue is that I have one b that I'd like to solve for that is in an exponent. If I wanted to get this b out of an exponent, I could apply a log to both sides. This b would be out of the exponent then, but now this b would be in a log. So I'm kind of stuck here, right? Either this b is up in an exponent or this b is going to be in a log. I can never just get out the one b from the exponent without also jamming up the other b in a typical or in another like setting that I can't get it out of. So from here, I'm going to say we now need help. There is no way for us to directly solve for our answer right here, but I can just give this to Desmos right here and have it tell me an answer that we're expecting to see. So now I'm going to pop back over to Desmos and see if I type this stuff in, what is it going to tell me is my answer here, or answers. I think in this case we can expect one answer. So negative 1 over 80b, so I'm getting here. So I can go to Desmos and I can do this. I can say to Desmos, listen, here's just an equation. So I'm going to do, let me make that. Okay, so I'm going to do negative 1 over 80 x is equal to e to the negative 0.05 x minus 1. And what we should see is that Desmos is going to pop us out some situations in which we're going to get a solution. You should notice this is green right here. Check this out. The first thing Desmos did is it plopped down a green vertical line at x equals 0. And you should notice that if we plug in 0 into this equation, we get 0 on the left, e to the 0 is 1, and 1 minus 1 is 0. So we overall get 0 equals 0. So it is true that one of our solutions is the integral from 0 to 0, in a sense, does this for us, but that's a stupid answer right there. It's not what we're looking for. Desmos is giving us another vertical bar out here. Hey, right where we were guessing we were going to see it, like 70-ish, 80-ish. Now, because this is a vertical bar, Desmos is going to be a jerk and not let me click on it to get like a point value of intersection right here. But if I keep on zooming in, I don't know, I can see that I'm getting like 78.4, at least is my like ballpark estimate for this guy right here. So Desmos is telling me with these vertical x location bars where the solutions to that x equation actually lived there, right? So I'm zooming way, way back out here, and we can see there's these two green lines on the screen, and these are telling me Desmos's answers to this equation, the numerical solutions to this equation. They cannot be algebraically determined, but Desmos has numerically determined that we can find numerical answers for these. So I think I'm comfortable stating my answer here as about 78.4, maybe a 78.41 is what I should be interpreting from Desmos for my answer here. So coming back over here, 78.41. So what our conclusion here is, if you ingest, or excuse me, if you are intravenously given a dose of a drug that decays pretty slowly, this 0.05 is a pretty slow decay rate right there for a drug to be in your system. Your kidneys and liver are mostly faster than that decay rate for most things. I'm just putting some numbers out here for this guy. But you should notice that when you are intravenously given a drug, all of it's in your blood immediately, and then your body removes it proportionally according to how much is in your body. That's why we get exponential decay of amounts in your bloodstream for intravenous use of drugs. All right. So in this case, it took us a little longer than 3 days, right? Like 78 hours instead of 72 hours for that to get down to being just an average of 5 milligrams per liter over all of the time that it's been in your system. The difference about intravenous drug, oh crap, sorry, I've been over here talking about this right here. At least I remember this time. So our difference that we want to identify right here is that when you are intravenously taking in a drug in your body, all of it is in your bloodstream all at once. It's right there right away. This is different as if you take a drug orally, right? If you orally ingest a drug or really ingest a drug any way that it's not directly going into your bloodstream, it takes your body some time to process this. This is even just like drinking alcohol, right? Even if you just like chugged a beer, for a little bit of time, it's actually just sitting in your stomach. And beer in your stomach does not get you drunk. Beer in your blood is what gets you drunk. It takes a while for that alcohol to make the transition into your bloodstream by way of things like lungs, stomach, intestines. Usually, those are the things that are extracting things out of what you've ingested and then putting it into your bloodstream. So when we take in anything non-intravenously, what you should anticipate is that rather than at time zero, we start at our maximum concentration. Again, like if I just take an aspirin, if I eat it, then at that moment in time, there is zero of it in my bloodstream because it's currently in my stomach. But what's going to happen over time is it's going to get processed and put into our bloodstream. But as it's going into our bloodstream, our body is like, what the heck is that? And then is removing it from our bloodstream. So, a more typical thing to include in these drug concentration formulas is that little coefficient of an additional constant multiple linear term sitting out front, an x or a t, because we're talking time in this case. What we're going to see graphically is that this is going to introduce that more of like a little like hump that we're going to experience rather than having all of it starting at your maximum and just decaying over time. That's not what happens when you eat an ibuprofen. It takes 45 minutes to an hour for it to actually reach the maximum blood concentration when it's having its most effectiveness. Then it's going to decay because your body is processing it and removing it from your bloodstream. All right. So let's go ahead and see the difference in graph. And let's go ahead and see the difference in calculus that's going to be really important for us today and for tomorrow particularly. So I'm going to pop back over to browse to the Desmos here. And so what do we got? 3t e to the negative 0.05t. So back over here, I'm done with this one. And we're going to do something similar to this here. Look for it to hunt for a solution to an equation for us, just to solve an equation that we can't solve. This was just algebra right here. But we're trying to get our calculus intuition from this guy. So I did something like 3t, or 3x, e to the negative 0.05x. And if I come back to the home screen now, what you can see, did I really do 3? Didn't I like change it to like 2 or something like that? I feel like I was getting a different, I think maybe that's like a little bit more appropriate for this. Whatever, it doesn't matter. I'm not super worried about that one coefficient right there. Did I not write this down? Am I not looking at the work I just did? Yeah, it doesn't matter. That's okay. So the point is here, hopefully you can visualize this as being a little bit more of what you picture our drug concentration, our bloodstream being when we eat something rather than when we directly inject something into our bloodstream. And I mean, honestly, I should just like directly compare these. Right? So hopefully you guys can see the idea that this purple decay one is saying we started at our maximum because this is our intravenous drug use. We are all of it's in our bloodstream all at once, and the only way it goes down, it changes, is by our body's kidney and livers removing it. Alternatively, the blue curve here is oral drug use. This is when we eat an ibuprofen. At first, there's none of it in our blood. None of it's acting on us yet because it's just in our stomach. It takes time for it to go from being in our stomach to our blood, and eventually it'll get to a maximum concentration. But once we've done that, and it's more at this point in time is where we reach the transition of more is being removed from our body, from our blood, than is being incorporated into our blood from our stomach, and so then it goes downhill over time. So this is a really typical form of function right here. This guy up top, our first one, it's a pretty typical family of functions, x e to the negative x, to describe drug concentrations in the blood, where we experience a rise for a while and then a fall. It's got to go from stomach into the bloodstream and then bloodstream removed by liver and kidneys out there. So we're still looking to play the same game right here. We just have a different function, right? Different medical use case right here. So what are we going to have here? Well, the setup for this problem is really, really similar. Honestly, I don't even know that I need to get a new great picture over here. We've got something now that looks more like this. We're picturing that we've got this average value right here. So one small thing to notice is I'm actually expecting that it's going to give me two different times that we were at that average value of the desired, what do we say, 5 milligrams. So same exact information as example 2. We're still looking to get back down to 5 milligrams as our average. But you should notice we probably will experience a 5 milligram average once on the way up while the drug is being introduced into our bloodstream. We will then also probably experience a 5 milligram average on the back end as far as, oh, now that we've been removing it for so long, we finally experienced that average of 5 at that point in time as well. So I am picturing a similar setup to the last one, but where we're going to experience probably two solutions to this. I think as the medical practitioner, I'm probably more interested in the second solution because that might give me information like when is it safe for me to give this person another dose of the drug that they're on, whereas this one probably not so much. But still, I'm expecting to find two answers now, and drawing a picture and making some guesses helps me to see that. So I'm picturing, we're playing the same ball game here. We're saying our average concentration should be 1 over b minus a integral from a to b of our concentration orally. So that's C sub O for oral instead of C sub I for intravenous right there. And again, the average is just a constant multiple times an integral. So there's nothing too crazy about what's happening on the right, but we're going to see that this is actually a little bit stickier than it seems. So same deal. I don't know how long I'm going for, but I know I started at 0. We're going from 0 to b of, I feel like I think just for the sake of making some numbers work out a smidge cleaner right here, I'm just going to make that a 2 because this is going to be hairy enough as it is right here. So just to make some nicer divisibility happening out there, it doesn't really matter. 2t e to the negative 0.05 t. I use that coefficient of 2 in the picture I put in Desmos as well right there. That's not really our big issue right there. So what is our big issue here? Well, our big issue here is that you guys can't actually do this integral yet. This integral is something that you haven't learned how to do until section 7.1. I'm going to do it right now, and I'm going to throw a little bit of early 7.1 stuff at you right now, just so that you can see it, because the point of this problem is this. You technically can't do this one integral right now, but the rest of this problem is going to pan out a lot like this guy back here. Once we do the integral, we're going to again land at a place where we can't quite compute an answer by hand algebraically. We'll still end up with an expression that we could throw into Desmos, and then we'll ask Desmos to find an approximate numerical solution for us. So the big strokes of this, broad strokes of this problem are the same. It's just that this integral right here, you need a new technique for. So let's kind of clean it up and see what's going on here. So same deal as last time. I am thinking to myself, I would like to divide this 2 away. It's just a constant multiple, so this will be a 5 over 2. And I'm also going to multiply both sides by b to move this over here. So I'm thinking 5b over 2 is equal to the integral from 0 to b of t e to the negative 0.05 t dt. Now the problem here is this. You don't know directly an antiderivative for an exponential times something else that's sitting right here, times t. Ultimately, what we're going to see is that while the u substitution was, in a sense, how do we undo the chain rule, there is no integral rules that are equivalent to the product rule and to the quotient rule, which is really unfortunate. This looks like what would be the product rule for integrals to me, but there's literally no such thing. So we need to very craftily rip apart this t from this e to the negative 0.05 dt. What we're going to discuss, so I'm just going to state this right now. We'll discuss the details of this tomorrow. But the integration by parts formula, the rule that we'll use, IBP, integration by parts, what this says is that if we can build an integral of u dv, that this is equal to u times v minus the integral of v du. So this is what we're trying to do right here is take a complicated statement and identify some alternate variables that we can use, u and v, that will help rip this integral that we can't do apart and make it a couple integral, or make it a different integral that we can do with some leftover pieces right here. So this is like a rephrasing of an integral. We're going to justify all of this tomorrow. I'm just going to use this for right now. So what my goal is here is to recognize that these two things are the same right here. This stuff right here, that is this stuff right here. What I want to do is identify how can I think of these parts as being a u and a dv, identify what are my missing parts like v and du, and then to rewrite it in this format. So here the way that I would write this is integral from 0 to b of t e to the negative 0.05 t dt. I typically say to myself, well, I know that I've got a u part here, and I'm going to want to know a du. I must have a dv part that I already know, and I want to infer from that what its v part must have been, so I can use that in my rephrased version over here as well. My simple setting here, and as we're going to discuss, some of our strategy according to doing our integration by parts is typically going to be choose for u a part that in a sense decays when you take its derivative. I know that e to the negative 0.05t, we don't really lose any parts when we take a derivative, right? But t just goes to 1. It got kicked down a notch. And so here I'm going to choose, trying to match up some parts here. For u, I'm going to choose it to be t. If u is t, then we can imagine that du is dt, right? That's like taking the differential on both sides right there. Now, if I chose my, and so video game cheater, we're going to talk at length that the hardest part about integration by parts is setting up like a checklist of rules for yourself. The cyclic ones exactly are the things that go in DV, and we'll see that we get some more complicated ones out there. But integration by parts is one of those things where it's like it's easy to do one case of it, but identifying different choices for like 20 different cases, there's a lot of options that'll crop up out there. So for dv, I'm going to pick, as is suggested, something that's more of our cyclic part here. So that's going to be my remaining parts. It's going to be my e to the negative 0.05 t dt. The d parts always get the d parts. The non-d parts always get non-d parts here. So I want to ask myself then, what would v have been? So I need to, since this is a differential, I'm thinking of integrating back up to get my v parts. So this should be a negative 20 e to the negative 0.05 t. And what you should see is that if we took this derivative, it would pop down a negative 0.05. Negative 0.05 times negative 20 is 1. So that's the exact constant multiples that we need to cancel that. I should also say 1 over negative 0.05 is negative 20. I think of that as a 1 over a decimal. It's just that negative 20 right there. So what this change of variable stuff allows us to do, this whole box over here allows us to do, is it allows us to rewrite this integral according to the integration by parts formula here. So what I'm going to get this is equivalent to now is u times v evaluated from 0 to b, u times v evaluated from 0 to b. So that's going to be t, let's write this a little, okay. Oh, I am going to leave it just like I had it right there. I'm not going to try and write this any weird. This is going to be t, that's u, times v, which is negative 20 e to the negative 0.05 t. That's all being evaluated because this was a definite integral from t equals 0 to t equals b. We're then going to subtract off the integral of v du. The integral of v du, we got a negative 20 e to the negative 0.05 t. And notice du is just dt. So the real important thing that happened here is, sure, this is a kind of gross expression, but this is actually integrable. You can do this integral just straight up right now, whereas this one you cannot. So the whole nice thing that we did, sorry, this is that got a little unreadable right there. There we go. Negative 0.05 t is what we got, is that power right there. Nothing weird right there. Just I wrote a weird looking decimal. So the point is we converted a non-integrable integral into some extra parts minus an actually doable integral. That was the bonus that we got out of integration by parts. We moved around our pieces, and now we can actually do this integration here. So let's go ahead. Now we just got to work to solve here. And notice we know that our left hand is this 5b over 2. So where are we at here? 5b over 2 is equal to, and now I'm going to clean some stuff up. So first part over here, negative 20 t e to the negative 0.05 t, evaluated from t equals 0 to t equals b. It looks like this is plus 20. Oh, and I forgot my 0 to b right here. Don't abandon your bounds. Plus, because we had two negatives, 20 I'm pulling out front, integral of e to the negative 0.05 t dt. And now I think we're ready to evaluate and integrate here. Oh, and I keep on forgetting my bounds of integration. 0 to b. Now again, we're going to end up with some b's that are up in a power. We're going to end up with some b's that are in the expression. We're going to end up with some b's that are on the other side. We won't be able to algebraically solve for b again, but Desmos will. So we can at least just finish doing the calculus parts, and we'll let the technology handle the algebra for us. So I'm noticing here, when I evaluate that b and then evaluate that 0, evaluating at 0, everything goes to 0 because that t being 0 will 0 out the whole thing. So I should just be getting negative 20b e to the negative 0.05 b. Again, this would be minus 0. I'll just write it here, minus 0. Plus, here I'm going to get 20. When I integrate this guy, I'm going to get another negative 20 e to the negative 0.05 t, evaluated from t equals 0 to t equals b. So all we're going to do is evaluate this guy, and we will have a full expression that we can throw into Desmos. Minus 400. Ooh, this is actually important here. Let me back up. Oh, come on, man, with that stuff. Oh, uh-oh. Don't start doing that to me now. Oh, man. Pen, you're good to me 3 out of 4 days of the week, Pen. Oh, my gosh. Yes. Okay. So my pen has these two little buttons on it right there. And it seems like it would be super useful to be able to press those buttons for like a undo, redo, or something like that. Except I slightly touch them by accident all the time. And then it's like, oh, what were you trying to get me to do right there? I'm like, stop, pen. I wasn't trying to get you to do anything. And they're the nicest buttons that aren't actually nice because I got fat fingers here. So what I was trying to do, okay, is being careful with this. Notice here, when we plugged in t equals 0, 0 times stuff was 0. But now over here, when we plug in 0, we're doing e to the 0 power, and that's not 0. It's going to be 1. So I'm going to keep this as, I guess I can still do like minus 400 here, but we really want to keep track of the fact that this is e to the negative 0.05b minus 1, because e to the 0 is 1. Yeah, so this is not a Wacom pen. This is a Huion pen, and I feel like exactly what you're saying. I'm trying to unmap them, and what it seems like is happening when I unmap them is they used to be like Control C, Control V, and it seems like I've been unable to map that they were C and V, but I think that it's still pressing the button Control with nothing else, and that's why it's doing strange things to me, like changing the magnification instead of the scroll. I agree with you. I got to just go look at my button settings here differently because I think it's just trying to press literally just the control button and nothing else, and that's obviously not what I'm looking for. So honestly, I think we're basically done here. I could technically clean this up a little bit more, but I don't know what value that stands for since all I want to do is just throw this expression into Desmos here. So this is what my mission is to put into Desmos. So let me just do it like this here so that we can just see it here. Window capture. Let me just add it. And let me just do it this way so you can actually see it. All right, let me throw that expression in here now. So I've got our original formula in blue. I'm going to go ahead and leave that. Right here is where I want to throw in our gnarly expression of interest. 5x over 2 is equal to negative 20 x e to the negative 0.05 x minus 400 e negative 0.05 x minus 1. So what we want to stop and say to ourselves is like, this is a crazy expression. How do you know that you're right? Like, it's so super weird for us to be like, yeah, I trust myself. I got this one. I don't know if that's reasonable for us to claim, but let's go ahead and stop and think about what we did here. Remember that when we were talking about our parts in our picture over here, what we said was we're kind of expecting that we should have one very soon answer because we should get to our average drug concentration of 5 milligrams per liter early, like as the drug is being introduced to our body. We should also experience it once on the downtrend, where after we've reached our maximum that we saw got up to like 17 milligrams per liter, we should again see an average of 5 milligrams per liter on the back end out there somewhere. When I then go and look at what I'm actually getting here then in Desmos, let me just switch over to only my Desmos view here, and I'll rearrange my screen orientation here. Get back to full screen action here. So now when I look at this in Desmos, I'm seeing exactly what we thought. I'm seeing we had our dumb stupid answer of 0. Got that one. I'm seeing that we get one really early answer here. And I'm seeing that we're getting one really late answer out here. Where out here we've reached that average height of 5 over the entire span of our function's time out here. So I'm seeing here, looks like our one sort of non-answer that just is coincidentally an answer because of algebra, that 0 should work, even though 0 doesn't give us the right answer. We saw our early answer here that's probably not the one of interest to the medical person of about 6 hours right here. So I could maybe say that about 6.1 is about one of our answers. I'm just trying to write these down so I've got them associated with our stuff right here. So I would say here, technology. So I'm going to just do this. And we're getting about 6.1. And we also are finding out here, if I go look much further out, for where our other time was that we, or the other amount of time we need to wait for to hit that average of 5, much, much, much further out there. I'm seeing about a 159.5, really close to exactly 159.5. Not exactly 159.5, but close enough for me to interpret that as my estimate here from Desmos there. So 159.5 might be my other answer here. So again, in this problem, I was technically getting a bit ahead of myself as to, sorry, let me remove this here. This was a problem officially me getting a little bit ahead of myself because this integration technique is officially what we're talking about in tomorrow's video, but it's so close to this week's stuff right here, so I chose to do it anyway. And again, all you guys can't do right now is just the stuff on the screen. You should certainly be able to draw the picture and set up the integrals that are associated with this problem as of today. You should certainly be able to, if I were to give you this integral expression, evaluate it, simplify it, and go to Desmos and find these values as of today. All that we still need to pick up tomorrow is what the heck is up with this formula for integration by parts? Where does it come from? Why do we believe it? How do we know when to use it? And what our appropriate choices are of variable substitution? I think that the hardest part of integration by parts is making our smart choices of u and dv to accrue the smart pieces of du and v to make in our rephrased expression that's over here. So integration by parts is one of those things that's, like I said, it's easy like once, but to see all the different things that can happen, it's very much an intuition dependence technique for you to have seen all the different things, exponentials, linear components, trig components, fractional and log components, all these different things that are going to come up out there. And in fact, now that I say log components, also remember, as my little reminder that I gave at the end of last week, is that you still don't know how to do this. We still don't even have an expression for that yet, the natural log of x, the integral of the natural log of x. We'll be able to do it with integration by parts. So there's a couple things that work out really nicely with integration by parts. So getting good at it will matter. I will tell you guys also, as my wrap-up statement here for the day, I did like pick out my homework assignment problems in my open math for the week for integration by parts. It's probably going to be one of the, it's not crazy long, but it's probably going to be longer than most all the homework assignments I'll ask of you from a single section all year. Integration by parts is maybe the one most important single technique that we get all year. None of these are good as a standalone technique. You got to learn all the parts of this class, but like integration by parts matters and it takes practice. So do anticipate that one being a little bit longer out there, but it's to make sure that you really see the fancy things that can happen. So tomorrow, we're going to justify why do we get the integration by parts formula that we do? How can we get a geometric sense for this formula right here? And we'll look at some complicated things that happen with integration by parts, including, and hopefully you guys are excited to hear me say this, hopefully this was gnarly enough for you right here. We're going to look at some scenarios tomorrow where you actually have to apply integration by parts 2 times to come up with an answer for an integral, and we don't even actually end up evaluating it. We sneakily backdoor it. It's called the backdoor or dump truck integration. It's a very clever technique. So integration by parts, really cool. We'll talk about it more at length tomorrow here. Yeah, exactly. That natural log one from the product rule right there. And while you're bringing up their video game Chester or cheater there, I will say there is in a sense a way that we undo the product rule in differential equations with something that we call an integrating factor. So later in differential equations. So now we're certainly, now not only are we not talking about today's content, we're talking about next semester's content, but here's another interesting little sneaky roundabout thing that we do in differential equations is if we're attempting to solve, for example, the equation, differential equation dy dt plus like 2y equals maybe e to the t, then here what we would do is recognize that this left-hand side maybe looks like that somehow came from a product rule, maybe. And I'm just thinking like when I see different derivatives and sums, I think product rule to myself, but it's not clear to me what. In differential equations, we'll justify that e to the integral of 2 dt is a special value. That's e to the 2t that can help us fix all of our problems here. So in differential equations next semester, in like our second week of class, we'll decide that to solve differential equations here, to find the function y that satisfies this, we can do something like dy dt times e to the 2t plus 2y e to the 2t equals, and then e to the 3t. And we can now end up seeing that what we really did right here is that this is the actual now product rule from the derivative of y e to the 2t. You should definitely see that in the first one, we took the derivative of y and left e to the 2t alone. In the second one, we took the derivative of e to the 2t and we left y alone. Equals our e to the 3t. Yeah, no kidding. Differential equations is more fun. In differential equations where we actually get to use all the stuff that we've learned here. And so things like this in differential equations make it a lot more exciting because in differential equations, we do want to look at things and literally be like, literally, I see an addition of two things that could be derivatives. Let's beat it with a stick until it's actually the product rule. And then we can undo the product rule and work our way back to what the original function was. Yeah, that's right. Yeah, good call. I do things like that all the time. Well, you brought up interesting things, and I can't not talk about them then. So a lot of this integration stuff is a lot of us saying, how do we write our expression in a different way so it does look like something that we can handle? This is a substitution up here. We took something we couldn't handle, and we rewrote it into something we could handle. Down here, this was an expression that looked almost like something we could handle. We introduced a new term so that it was something that we can handle. A lot of this stuff is about kind of forming those kind of alternate perspectives to make that happen. Our first exam, I think what I kind of had worked out was that we're going to do most of chapter 7 before we take our first test. So this week we're getting 7-1. I think next week we're doing 7-2 and 7-3. And then I think we're still going to do like 7-4 and 7-5 and look at a test. What I need to decide is what is sort of like the last piece of content that's going to be covered up through the test. I think it might be that we're going to go, this is my estimate right now, but my estimate is that we're going to cover up through 7-3, and that will be what's on the first test. So that's still sort of 2 weeks worth of material, but actually 3 weeks of like time before we take that first test is what I'm estimating right there. So we won't quite finish chapter 7 before we take a test. We'll hold off on the last topic of chapter 7 before we take our test. So still a couple of weeks, but in a sense, kind of coming up soon right here. And I'll talk a lot about. I'll make sure to get that information out in Canvas and stuff. That test will be like in a take-home setting to where you guys will have like a day or 2 or 3 days or something like that to work on it at home. I'm debating if I want to make it have like maybe even like a smidge of like my open math questions versus some written questions so that I could have, it's hard for me to grade 10 pages of digital work per student kind of thing. But very obviously on tests, I certainly want to see solutions and not answers and actually see your work for some things like that. So we'll be sure to talk about all that, but it won't be anything that's like you all need to take a test between 2 o'clock and 4 o'clock on this day. I'll make sure that it's certainly got some like broader time than that. And honestly, you guys are all beyond taking math classes at this point anyway in life to where you could do anything meaningful in an hour or two. It should be more like go home and sit down and think about it over a day or two anyway. So the test will certainly be of a format that is friendly to you in that sense right there. So we still got about 2 weeks, and I'll make sure that you guys all have what you need to know for that coming up here. So yeah, so those are the examples I wanted to hit up today. We got a little bit ahead of ourselves with a 7-1 example for tomorrow. But again, that was just the integration step. The concept of thinking average value is still applicable there. I technically did a little bit of the calculus for you in example 3, but we still hopefully could have pieced together the other parts on our own right there. So we're going to talk integration by parts tomorrow. That's our stuff for week 4 here. And then we'll keep on going with some more of our integration techniques. We're going to get like our inverse trig integrals and a bunch of good stuff like that. Kind of wrapping up our integral story of what are the basic integrals that we don't know how to do yet. We're going to get the rest of those here in chapter 7. So very cool. I will see you guys for some integration by parts in the next video here. Have a good one, everybody. Yeah, average values, I'm hoping your takeaway is, oh, okay, that was pretty easy. The book literally covers it in like 2 pages. It's not that much. Integration by parts, I think, is where we should be spending 70% of our time and effort this week here. So good. I'm glad you feel that way too. Cool.